Pleasure to introduce Ali Raad from the University of Glasgow, who will be speaking first, even though we claimed he would speak second because there's been some technical difficulties. And he'll talk to us about the existence and uniqueness of inductive limit Cartan subalgebras in inductive limit C-star algebras. So go ahead, please, Ali.
Thank you. Thanks, Karen, a lot. And thanks to the organizers for this great opportunity. It's my first time virtually in the Czech Republic and Prague. I've been here physically twice before. It was always a good experience. Hopefully in the future I can visit physically again. Yeah, so the title of my talk is quite long, and I'll be explaining these terms throughout the talk. But basically it's the main results of my PhD, and my PhD was supervised by Xin Li. I just thought I should say that from the start. Okay, so let me just start with the outline of what I want to talk about. So firstly, I just want to give a motivation about Cartan subalgebras, why I care about them and why people generally care about them. And then I want to just go through some of the preliminaries and highlight those with some examples in order to understand the rest of the talk. And then I will go through the main results, and each step will kind of be an increased level of difficulty somehow. So we start with the AF algebras, then AI algebras, AT algebras, and finally, if there's some time, I would like to generalize some of the findings to certain topological spaces X. And lastly, I will just talk about some consequences of all of this. Okay, so why we care about Cartan subalgebras, where there's many reasons, but recently there's been a connection between topological dynamics and geometric group theory via Cartan subalgebras to C-star algebras. So we all know how to get a C-star algebra from a topological dynamical system or a group. But it's exactly the Cartan subalgebras that allow us to reverse this procedure. This is mainly, due to work by Xin Li, for example, a couple of years ago, where you can capture the notion on the left using continuous orbit equivalence, and on the right via quasi-isometry. And so somehow the Cartan subalgebras, So somehow the Cartan subalgebras are the key link that link all these fields together. Another reason which has been of interest lately is the relation of Cartan subalgebras with classification and some of the problems there. So, for example, the famous UCT problem, which asks whether separable nuclear C-star algebras satisfy the UCT, has had many, reformulations and reductions over the years. And one of these is whether certain C-star algebras contain Cartan subalgebras. So I don't want to go into the detail here. One can give more than one talk about this. And this is not the emphasis of my work, but at least people are really getting interested in this because of these types of questions. So there's been many results about the existence of Cartan subalgebras, and this is not an exhaustive list, but I just mentioned some of them. So one could say that Xin Li and Jean Renaud were the first to maybe kind of systematically study the existence of Cartan subalgebras and C-star algebras, and they found Cartans in, for example, C-star algebras of many connected Lie groups, nuclear row algebras. Barlach and Raum were able to classify Cartan subalgebras of dimension drop algebras with co-prime parameters. And recently, Xin has shown that every classifiable simple C-star algebra has a Cartan. So these types of questions about existence and uniqueness are getting more and more attention. My PhD work has been about these existence and uniqueness questions, but for inductive limit Cartan subalgebras, which I'll explain what those are precisely soon, and in certain inductive limit C-star algebras. Okay, so I've been saying Cartan subalgebra over and over again, so it would be good to just see the definition. So we will call a C-star subalgebra B of a C-star algebra A Cartan subalgebra. If first of all, B is maximally commutative inside A. You wanted to have an approximate unit for A, and you require that it's regular which just means that if you take this set of normalizer elements, so all of the elements in A which normalize B, you want this to generate A as a C-star algebra. And finally, there should be a faithful conditional expectation from A onto B. So let me just highlight this definition via a classic example. So if we look at Mn of C, say, then we can just take the diagonal subalgebra, and that's an example of a Cartan subalgebra. I mean, it's clearly maximally commutative. It contains the unit, so all these points are pretty trivial to check. The regularity might be a bit more tricky, but one can note that the standard matrix units Eij, these will normalize the diagonal. So and the matrix units do generate MNC as a C-star algebra. And the conditional expectation can just be given as a projection onto the diagonal. So this is quite straightforward. And when I say unique, I mean, of course, up to isomorphism. You could have different Cartan subalgebras, but they will all be n-dimensional, and you can map the basis elements, from one to the other, and that gives you the isomorphism. Of course, I mean, there's nothing special about one stamand. We could look at any finite dimensional C-star algebra, and this will just be a direct sum of matrix algebras, and just take the diagonal subalgebra as an example. Yeah, so this is again a Cartan. Well, I don't know why I'm kind of going up the ease scale rather than the difficulty, but any commutative C-star algebra is a Cartan subalgebra, because it itself is a Cartan subalgebra. And then maybe some non-trivial examples that you can find in this paper by Lee and Renaud, where you, like I said before, you can find Cartan subalgebras in the C-star algebras of many connected Lie groups, in nuclear row algebras, and some non-examples. So there's no Cartan subalgebras in reduced group C-star algebras of non-abelian free groups. Right. Another notion that we will need is that of an AX algebra. So you've probably seen this before, but I'll just give the definition anyway. So I'm looking at inductive limit C-star algebra, written like this, where this AI we call the building block, and the phi I the connecting map for the inductive limit. And the building blocks look like direct sums of matrix algebras with entries in CX. So X is just some compact Hausdorff space now, but if I let it be the point, a singleton, then I retrieve the AF algebras, which are just where the building blocks, of course, are just direct sums of matrix algebras. If X is the unit interval, then we get what is known as an AI algebra, so I for interval. And when X is T, we get the AT algebras. And from this notion, we can define the concept of an inductive limit Cartan subalgebra. So once I have an AX algebra A, written as above, then an inductive limit Cartan subalgebra, first of all, is a Cartan subalgebra of my inductive limit, but it takes a specific form. So it itself is an inductive limit of some BIs with the same connecting maps phi i's, where these BIs each are Cartan subalgebras of AI. So somehow this is the canonical way to build a Cartan in the inductive limit, by taking a limit of Cartans in each block. So let me give an example from a construction which basically dates back to the 70s by Stratilla and Voculescu. So you can consider the Carr algebra, so M2 and M4 and M8, etc. These are all multiplicity 2 embeddings, and then you just take the diagonal subalgebras in every building block and take their limit, and what you get is a canonical type of Cartan subalgebra. Okay. Another notion that we will need later, which will be related to Cartan's, is that of a maximally homogeneous subalgebra. So if I have an abelian C-star subalgebra B, say inside CX tensor Mn, it is called maximally homogeneous if the dimension at every evaluation of B at a point X, for every X, is maximal, so which is N. I mean, if you evaluate B at a point, you get some subalgebra of Mn, which is commutative, and the maximal dimension for that is N. We just require that it is N at every point. And related to this, but for star homomorphisms, is the maximal homogeneous star homomorphisms, where if you have a unital star homomorphism between CX tensor Mn into CX tensor Mm, it will be maximally homogeneous if when you evaluate the image algebra at every point X, you get the maximal possible dimension as a vector space dimension. I mean, all of these are as vector spaces, which is N squared M over N. I mean, of course, this is NM, but writing it like this kind of shows more what's going on. If you forget the CX here and just think of this as in the classic kind of AF setting, then we know Mn embeds into MM M over N times. But there you don't, I mean, you see the same copy just again and again from the domain. Whilst when you have these continuous functions, you can have kind of the copies can be distinguished somehow. And each copy will have at every evaluation dimension N squared, and that's where you get the N squared from. So let's look at some examples. Again, for the first notion of maximally homogeneous subalgebra, we can just take the diagonal subalgebra, CX tensor Dn inside CX tensor Mn. Of course, at every evaluation, this is just Dn. And for the map, well, we could take a map like this, where you copy A M over N times in your codomain, and you precompose every copy by some continuous function x to x. And if all these functions are pointwise distinct, for example, then you will get a maximal dimension, basically. This will give you N squared M over N. I'll kind of go into more about this map on the next slide, I think, because this is important. Yes, so these types of maps are called maps of standard form, as they will play an important role. So these, again, I just write it more nicely, are maps of the form CX tensor Mn into CX tensor Mm, where you copy a matrix diagonally and precompose by some functions. Of course, all of these notions can be extended to direct sums as well, but in the natural way. I just didn't want to add it here because it just makes the notation a bit more technical. Okay, so this is basically most of the stuff we will need in order to look at some of the results. So for the AF algebra class, the existence of these inductive limit Cartans was already well known. And due to work by Stratilla and Voiculescu from '75, effectively what they end up getting is that you can create these inductive limit Cartan subalgebras in AF algebras, even though they weren't called that. And
just a quick interruption. There's a question in the chat.
Oh, sorry, I cannot see the chat.
The other Ali, who says, B is a subset of C of X tensor Mn. So what do you mean by B of X? You mean Bx for every B in B?
What here?
Yes, exactly. When you say dimension of B of X. So
yeah, so X is a point. I mean, this can be identified, right? B can be I mean, CX tensor Mn is continuous functions from X into Mn, right? Yeah. And you evaluate at the point X, and you get some subalgebra of Mn. Mm-hmm. Right? And you take its dimension as a vector space, basically. Did that make sense?
Yeah. So what I was saying is that B is a subset. So so I mean that each element of B act on X. This is what you meant.
No, so B is a C star subalgebra of C
Of C of
extensor
X
Mn.
tensor Mn of A. So it is
Yeah. It's a C star
Okay.
subalgebra of that, yeah. And it's abelian, and you know, C extensor Mn I can identify with continuous functions from X to Mn, right? It's yeah. I'm kind of I didn't state the identification, but there's that identification going on. Yes.
Oh, I see. Thank you.
Yeah, no problem. Thanks for the question. Right, so we're here. Yeah. Okay. So their construction basically gives us an inductive limit Cartan subalgebra, and the proof is quite nice and short. So I'll just include it quickly. It's an inductive proof. So if you have already identified a Cartan subalgebra Cn inside the nth building block An of your AF algebra, and if phi n is your connecting map, say, then you get the next Cartan by declaring it as the C star algebra generated by the image of the previous one, and some subalgebra Dn plus one. What is Dn plus one? It's just chosen to be a Masan, the commutant of the image of phi n An. So I mean, as you can see, Dn plus one commuting with phi n An means it will commute with phi n Cn, and phi n Cn is abelian because Cn is a Cartan. So this is indeed an abelian C star subalgebra. And by the choice of choosing a maximal abelian thing in the commutant, you get the maximal abelianness of Cn plus one, and then you can check all the other properties to ensure that this is a Cartan. And then just take a limit with the same connecting maps, and what you end up getting is an inductive limit Cartan subalgebra. But a nice question to ask, which is one of the first questions I started with, whether this construction is unique. So what does uniqueness mean? It will mean that if I can get another inductive limit Cartan subalgebra D, I should be able to find an automorphism of A which maps C onto D.
I'm sorry.
Yeah.
I beg your pardon, Ali. What's the base step? Which is the first Cartan subalgebra that you choose in order to start the construction?
Right. You can just take the diagonal, for example. You can choose any of your choice. Yeah. And again, the reason one wants to ask about uniqueness is exactly this, because you could have a different base step, and you could have different DNs here a priori. And so technically, I mean, you could get a different, inductive limit Cartan subalgebra. And the question is whether they're actually all isomorphic. So yeah, good question. And the answer is yes, they are. So it boils down to this theorem here, which is if you give me A and B to be unital AF algebras with some inductive limit Cartan subalgebra C and D, then we have the following equivalence between isomorphisms of K theory and these Cartans. So the K theory is isomorphic if and only if there's an isomorphism of the C star algebras, but it also sends, you can choose the isomorphism to send one of your Cartans onto the next one. So this is Elliott's classification theorem, basically, for AF algebras, but with this additional feature of taking care of the Cartans. And uniqueness follows from this because, of course, if A is B in this setting, then just choose alpha to be the identity map. And this is saying I can find an automorphism of A which maps any Cartan onto any other one. So that settles that, basically. Okay, so this was the AF algebra class. And now the next level was to study higher dimensional things like AI algebras. So I'll start off with the actual punchline, so the theorem, and then I'll try to explain how I get there. So it turns out to be true that every unital AI algebra with unital and injective connecting maps contains an inductive limit Cartan subalgebra. And here, the main ideas are as follows. So we're looking at maps of this form, right? So C01 tensor Mn into C01 tensor Mm. In fact, we're looking at direct sums of such things, but for the purpose of understanding the main ideas, it doesn't really matter. So we have this this iota here, which is just the canonical generator of C01. So just the map that sends T to T. And then due to work by Thomson in the 90s, he basically showed that when you have two connecting maps of this form, say phi and psi, and you look at the image of those maps on iota, and then you evaluate them at every point T in 0, 1. You'll end up getting some matrices, and if these matrices share the same eigenvalue set for every T, then the original connecting maps phi and psi must have been approximately unitarily equivalent. So this is very useful for us, because now what I can do is, if you give me some arbitrary connecting map here, I can construct a different map which has the exact same pointwise eigenvalue set as my original one, but it has a nicer form. It has that standard form that I talked about, which is where you embed things diagonally and precompose by certain functions. So now if I replace my original maps of the limit by these ones, and these are approximately unitarily equivalent to the previous ones, then by Elliott's work, it means the inductive limit C-star algebras are isomorphic. So I can just assume that my maps had this nice form to start with, and then constructing inductive limit Cartan subalgebras with such maps is much more straightforward, basically. Whenever you have something that kind of embeds diagonally, it's always much easier to construct these inductive limit Cartan subalgebras. So that's basically the main ideas of the proof. If you want the details, it's in a paper that should come out pretty soon, but you can find it on my homepage. All the ideas in their full technicality is there if you care about the steps of the proof. So it still remains to answer the question of uniqueness for this. So it turns out not to be the same as the AFKs. As you can imagine, I mean, this is a dimension 1 higher, so the level of complexity is just different. And uniqueness will fail, and it will fail due to the following observation, which is basically, you want to study the spectrum of the Cartan that you get in your AI algebra. And in order to understand it, I mean, if you understand it well, and you can show, say, that some AI algebra has two inductive limit Cartan subalgebras with non-homeomorphic spectra, then you're done, because you've shown that the spectra are not homeomorphic, so the Cartans could not have been isomorphic. But so how does the spectrum look like? Well, it turns out to be a disjoint union over all the Bratelli paths that you get when you, I mean, corresponding to your inductive limit. And each component is just an inverse limit of the unit interval. So it's basically a counter set with fibers, some inverse limits of the unit interval. And the main idea is to get this. So apologies if you have not seen the correspondence between Cartan subalgebras and étale groupoids before. It won't be important for the next slides, just for this. But if you have, then this is the idea. From Renaud's theorem, basically, Renaud's work, you can get a correspondence between Cartan pairs of C-star algebras and twisted étale groupoids. So the C-star algebra corresponds to the reduced groupoid C-star algebra of your twisted étale groupoid, and your Cartan corresponds to some continuous functions, C0 functions on the unit space of the groupoid. So if I have some inductive limit Cartan subalgebra, C here, then I can form the correspondence with the groupoid picture, and I will get some twisted groupoid C-star algebra here, C-star G, and the Cartan just corresponds to C0x, but X is obtained nicely as the inverse limit of the unit spaces in every block, basically. So by understanding the unit space in every block of my AI algebra, I can understand the spectrum X in the full thing. And from this, you can basically start looking at all the possible Bratelli paths, right? Infinite paths when you draw the Bratelli diagram. And this is kind of like the AF algebra case, except that the arrows can be labeled by the continuous functions that appear in the diagonal of the standard maps, basically. And that's what I meant by it's a disjoint union over all these paths, all the possible infinite paths, and your inverse limit over 0, 1 is with respect to whatever functions are on these arrows, basically. It's a complicated spectrum, but it's very useful in order to understand this uniqueness property. And from this, then you can construct an AI algebra like this one here. So this is kind of the AI version of the car algebra, but you construct it in such a way that one of your inductive limit Cartan subalgebras C has spectrum containing a singleton connected component, whilst D does not. And in that way, you get non-homeomorphic spectrum and thus non-isomorphic Cartans. And the explicit construction is like this. I mean, you're going to embed A twice into the next, into the codomain because of this 2 to the n. And you can choose your functions. Like I said, these functions have to be functions from 0, 1 to 0, 1. So in the first construction, I choose my functions f1 here to be just the constant map 1. And the blue function f2 will just be this 10th map here. And you repeat this again and again. As for the other construction, you choose your red map to be to have first half to be like the 10th map, but then becomes the constant 1 function. And your blue map to be the constant 1 function, but then becomes the second half of the 10th map. Why am I doing it like this? Well, like I said before, by Thompson's work, if you evaluate pointwise these maps on the canonical generator of the center, then you just get the eigenvalues will just be the points here, basically, and at every vertical line here, it's exactly the same set of eigenvalues, regardless whether you're in the first or second setting. And so this tells me that the maps in both constructions are approximately unitarily equivalent, and so the AI algebra is the same that I get. However, once I try to understand the spectrum, if I keep going along the Bratelli path, which is just f1, 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 and so on forever, then you take an inverse limit of 0, 1 with the constant 1 map, and that just gives you a singleton. Whilst if you take any combination of inverse limits from these maps here on the right, the red or blue, in any way, you will always get 0, 1 as your inverse limit. And that's why you can conclude that the Cartans are not isomorphic, basically. Okay, so that settles the AI question. And then one wanted to look at if the same can be said for the AT algebras. And so whilst you can still get that your connecting maps are approximately unitarily equivalent to those of the standard form, the problem is that the unitaries that witness the relation are over 0, 1 rather than the circle. And it's in such a way that everything agrees at the endpoint 0 and 1, but the unitaries themselves do not have to live in C of t. And in that way, I cannot kind of ignore them in my inductive limit and say that the maps are of diagonal form. So one had to look at other ways to go about this technical issue. And it boils down to the observation that AT building blocks of this form CT tensor Mn, in such building blocks, the notion of being a Cartan subalgebra is the same as being maximally homogeneous. Remember, this maximal homogeneity was about you evaluate at a point and you get maximal dimension. So these two notions are the same here. And so we've transformed the problem into that of maximal homogeneity, for which there's a lot of work done about connecting maps on AT building blocks, which are maximally homogeneous. So this is useful, and what you get is, as in the AI case, you do end up getting that you have inductive limit Cartan subalgebras. Just the proof is a bit different. So here, like I said, the main idea is that you're looking now at maps of this form, and you can perturb those to ones which are maximally homogeneous instead. And then you extend this to direct sums, because the first part was already done in Elliott's paper in '93, when he was looking at classifying real rank 0 inductive limit C-star algebras. But the direct sum is kind of the novel thing, which is it's not as straightforward as one would think. And then the maximally homogeneous maps that you get will be unitarily equivalent to those that take a standard form. But like I said, the unitary is over 0, 1. But you can use that information to find the following out. And this is built on work by Thomson, where he studied such maps between AT building blocks, which were maximally homogeneous. And then if you have a maximally homogeneous subalgebra in A, C, then you can always find a maximally homogeneous subalgebra D inside B, such that D is the C-star algebra generated by phi of C and the center. So this is looking a lot like Stratila-Voiculescu type construction, which was very useful. And then you can take a limit, like in the same sense as Stratila and Voiculescu, and this is how you get your inductive limit Cartan subalgebra. Of course, here uniqueness will fail in essentially the same way as for the AI case. Every AI algebra is an AT algebra, so I can just transform the whole construction into the circle language. And it's the same example that does it. And finally, the idea was to see whether this could be generalized to just certain topological spaces. And it will work if I assume X is a finite connected planar graph in C, which will generalize all the examples I had before. So of course, the interval is just a graph with 2 points and an edge. The circle is like the triangle graph. And for this, you end up getting that every unital AX algebra with unital injective connecting maps contains an inductive limit Cartan subalgebra. The main ideas here was to look through the proofs of what we did for the AI and AT case and kind of highlight the essential topological ingredient that we were using to get all of this done. And it turns out that most of the results that we were obtaining work precisely because we have a universal cover for our space, which has vanishing check cohomology. So that was really the key point. And of course, these graphs that I'm considering have trees as their covers. And these will be locally compact contractible, and so they will have vanishing check cohomology. And then the equivalence between Cartan subalgebras and this notion of maximum homogeneity extends to compact Hausdorff spaces X. So the same notions can be applied there, and that's how you get these results. Okay. So that was the bulk of the work. So what this does now is cover a lot of ground, of course. I mean, there's a lot of C-star algebras that are AT algebras, like the Bun's dead ends algebra, rational rotation, many cross-product C-star algebras. These are all AT algebras, and so we get this existence of inductive limit Cartans for these. And then you can also think about probably the biggest class to generalize, which is AH algebras. I haven't defined what these are, but they look like AX algebras, except you're looking at corners of the blocks. You're allowed to multiply left and right by projections. So there's a result by Gong and Lin and a few others, which says that if these AH algebras have the ideal property and torsion-free K theory, then they are in fact AT algebras. So we can find Cartans for these. Of course, the next question is whether once you remove this torsion-free K theory, what happens? And this is kind of a work in progress. And another point to take home, which is probably the most important thing about the construction, is that the connecting maps that we start off with are arbitrary. and we do some magic and turn them into nice maps, which allow us to construct Cartans more easily. In a lot of other settings, like for example, in Shinli's work, where he finds a Cartan subalgebra in the Jiangsu algebra, or there you already have predefined connecting maps. So this technique of just changing the maps you have to something you like could be generalized to perhaps these AH algebras with just the ideal property. And anyone who works with classification, simplicity is almost always assumed. Here we don't care about simplicity, which is good. And of course, because the construction is explicit, you can start to build up groupoid models for these Cartan subalgebras that you get. And all of this is the type of work that I'm currently doing, that I'm doing now, and will continue to do until hopefully either there is no answer or there is an answer. But yeah, that's all I had to say. So thanks a lot.
So thank you very much, Ali. Since we're a bit late starting, if it's okay, maybe we can save the questions till after Zara's talk.
Sure.
I think there's a quick
That's
one
fine.
or two now. Tristan, you looked like you were about to say something. No, I can't see you, find you.
No, nothing to say. Yeah, it was a good talk.
Yeah, okay, so Zara, do you want to try to share your screen, and we'll hopefully have no major IT issues.